Alright, thanks for coming to my talk. My name's Damien George, and I'm a theoretical physicist working at the University of Cambridge. And last year I had this idea to rewrite Python so that it would fit on a microcontroller, and I did a Kickstarter which I talked about yesterday. So this talk today is about the internals of MicroPython and how it differs from CPython, and what its benefits are and what it can be used for. So I need to focus. There we go. Okay. So nowadays you can buy very, very small chips that have a lot of functionality on them. They have a whole computer, RAM, ROM, lots of peripherals on a tiny little package. And with all the sophistication comes obviously sophisticated programming. And you have to do most of this in C. So wouldn't it be better if you could do it in a scripting language like Python, for example? It would help you develop your products a lot quicker and debug and make more sophisticated high-level control for these controllers. And microcontrollers are used in everything, in your toaster, your washing machine, in your car. There are more microcontrollers in the world than computers. So they're actually a very important part of the computer ecosystem. So my question that I had was that I asked myself, is it possible to make Python run on a microcontroller? And actually there have been a few attempts before. I won't really have time to talk about those. You can ask me later. But why is it actually hard to do this? And the main answer is that there's very little memory on a microcontroller. And Python uses quite a lot of memory, and so do many other scripting languages. So the main aim of MicroPython is to make it run in very little memory. And in answer to one of the keynotes before, the stance of MicroPython is Python 3.4, not Python 2.7. So it implements 3.4. Okay, so just so that you understand what it is, I thought I would do a little demo first. So I'll have to use this microphone. So this is one of the boards here, and it just plugs in via USB into your computer. Okay, so it's now running Python on the board. So I will. Okay, I can connect using a serial terminal. Okay, so now I've logged into the board via a serial communications program. It's just a dumb terminal sending characters and receiving them over the USB virtual COM port. Okay, and I see here I have a Python prompt straight away. So I can do 1 plus 2. Now you can't see the answer because the screen's cut off there. Say percentage 1 plus 2. Okay, there you go. Now you can see it. Okay, so what happens when I type this in is that there's nothing on the computer being done. It's just sending characters to the board. The board then compiles and executes that piece of code on the actual microcontroller itself. Now you have, okay, so unfortunately, how will I make this so you can see it? Okay, DWM is very useful. Now, okay, so it has floating point number support, it has complex numbers, it has everything you want. I mean, it's really Python. You have big num, you have big num converting to floating point, or big num proper division. So all of the features of Python are actually there. You have generators, you have classes, you have all of the standard Python exceptions. Now if I can do a soft reset here and it just resets back to nothing, I can show you how much memory it's actually using. So the number 528 there on the third last line, that's the number of bytes of RAM it's currently using after a soft reboot. So 528 bytes of RAM. I can do 1 plus 2 and then have a look again. 752 bytes. I can. So there's the GC garbage collect and then have a look back down to 592 bytes. So it's using very little memory. I can make, say, a big list. Again, that's probably too much. Okay, and then it's using 60K RAM now to hold that 10,000 element list. Okay, so it's running Python and executing code directly on the board here. Right, so that's the end of the demo. I can show many other things, but there's lots of things to talk about first. Okay, so why did I choose Python and not, say, Ruby or JavaScript? Well, because it has a lot of high-level features that are very useful, list comprehension, generators and exceptions, and it has a very large existing community, as we see before us, so that's very useful to teach people how to use it. Python, I'd say, is very easy to learn, but at the same time it's very, very useful for people who are familiar with programming to get a lot of work done very efficiently. It has a lot of powerful features like generators and yield from and classes and lots of hooks that you can do with special methods. It's a very powerful language when you get into it. It's actually ideal for microcontrollers when you look at it from a certain point of view. It has native bitwise operations like AND and OR, like you do in C, and you want to do ANDing and ORing in a microcontroller environment all the time because you've got to play with bits here and there to turn things on and off. Procedural code is very natural when you're programming a microcontroller because you want to do things and you want to have an effect on the world. There's a distinction between integer numbers and floating point numbers in Python as opposed to, say, JavaScript. That makes a big difference on a microcontroller because sometimes you really want an int and sometimes you actually want a float because floats take a lot more processing power and so on and more RAM. And there's actually a lot of opportunities for optimization within Python. And that's because Python is ultimately a compiled language, so you can take advantage of standard compiler techniques to optimize things. For example, we have constants in MicroPython, so you can declare an identifier to be a constant number, an integer, and that will be substituted in the compile stage. And so there's lots of tricks that we can actually do there. Sometimes we have to, say, give up the fact that, okay, you're not allowed to redefine the range identifier so that we know that range is always going to be an iterator. And then we can do a lot of optimizations there. Okay, so why can't I just take CPython and recompile it with size optimization and on GCC and then just put it on the microcontroller? Or PyPy, for example. So, fitting it in a binary on the microcontroller is one thing, but actually it's really the RAM that matters, so the amount of RAM that's used. So in CPython, a single integer, the number 1000 or something, takes about 16 bytes of your memory on the heap, not on the stack, on the heap. And for optimization purposes, CPython will, when it boots up, or when you type Python, before you actually get a prompt, it will pre-create 262 of the integers, the small ones, between -5 and +257. And that takes about 4 kilobytes of RAM already. And on a microcontroller that only has, say, 64 kilobytes of RAM, you're already taking up a lot of your useful RAM there just by having the numbers 1 to 256. You could put them all in ROM, but still you're taking up a lot of ROM doing this. And any integer outside of the pre-allocated range takes up more RAM. The other thing in CPython that takes RAM that hurts you sometimes is whenever you do a method call, you need to create an object on the heap, which is the binding of, say, the subject here, LED, and the method on. So it looks up on in the method table of the class instance, and then binds that method to the object LED, and then you call on that object. And that takes 20 bytes on the heap just to make that bound method object, which you throw away straight away after you've called it. So if you want to do, say, turn an LED on, LED.intensity 1000, you'd need 36 bytes of heap RAM just to do this, which is something that you'd probably want to do with no RAM. You can use a stack, but no heap. For loops also require the heap to create a range iterator object. So if I just want to do a simple loop, turning my light on and off, it's going to require RAM, which is not something you can tolerate in a microcontroller environment, because you may be executing some of your code on an interrupt. So say, microcontrollers, you have low-level access to interrupts, and you say, when the timer expires, I want to execute this code, and I want to have that preempt any other code that's running. So I'm running my main thread, and then the interrupt comes along, and I go along, and I want to execute some code to, say, flash a LED, and I want to do that without allocating heap RAM, because if I'm in the middle of garbage collecting in my previous thread, I can't touch anything in the heap. So I've got to be able to do a lot of stuff without allocating RAM. Okay, so if you ask me about any piece of the code, why is it done like that, I'll probably say to minimize RAM usage. And that is apparent throughout the whole code base. So the strings are all interned. That's done in CPython as well. Small integers, so the way I was describing before, that an integer requires 16 bytes in CPython. In MicroPython, you stuff it into a pointer, and I'll explain about that shortly. Thanks to PyPy, we use the optimized method call where we don't have to make a bound method object. So we took a hint from them, which is great. If possible, we optimize a range object, so if you do 4x in range 100, it actually turns that into just a normal while loop incrementing x, but still with the same Python semantics. That way you don't need any heap memory. You don't allocate heap memory when you do a call. All of the stack frames live on the C stack, so all the MicroPython stack frames just use a little bit of stack on the C stack. Anything that we can ROM, we put in ROM. For example, modules, dictionaries, anything that you can pre-create in ROM, we do that. So importing, say, the OS module requires nothing more than just creating a new link to say that, oh, I've imported the OS module and it's now available. The actual OS module itself is completely in ROM. We don't have reference counting, so that takes out one word of memory from each object, and also means that you don't have to incref, decref all throughout the code, so that saves a lot of code space. And because there's only, say, 100K, 200K RAM on your microcontroller, doing a mark sweep garbage collection takes 1 or 2 microseconds, and it's always a very small time. You can also disable the garbage collector if you need to. Exceptions are implemented with the custom variation of set jump and long jump. So in CPython, they're implemented just by returning null and checking null all the time. So with the philosophy that exceptions are things that happen exceptionally and not often, it's best to optimize that by saying, okay, most of the time we don't need to check for an exception, only when it happens do we do. And so using set jump, long jump is a smart thing to do there. So when an exception happens, you've got to do a bit unwinding the stack and going back to the sort of the thing that you can catch, the part of code that will catch it. But that doesn't happen that often, so it's optimized. It optimizes ROM as well as RAM. And it's quite efficient as it is implemented. So the actual internals of the MicroPython framework. So it's like most other compilers and interpreters. You have a lexical analyzer at the first stage, which splits the stream of your script into tokens. It interns all the identifiers it finds. Most of them are already interned in ROM, so a lot of the time, def and all the keywords and most of the inbuilt classes and method calls and function names, they're all pre-interned into ROM. So when you type in your code, a lot of it doesn't need any memory once it's parsed. The parser is written in a way to minimize RAM and ROM usage. It's it's represented in a table, which is then interpreted by a single function that's non-recursive. You can have a look at the details if you like. So the compiler, to minimize memory, it uses the same parse tree and goes over it 3 or 4 times, doing different things each time. The first time it computes the number of locals, the second time it computes the stack size, the third time it works out labels, and the fourth time it emits the code. The code emitter is connected to the compiler, so in the last stage when I want to emit the code, I can select to emit bytecode, like normal, sort of like CPython bytecode, but it's a variation of that. It's compressed and optimized. But MicroPython can also emit machine code. So what it does is, instead of emitting a bytecode, say load fast, it emits the equivalent machine instruction, move register to memory, or move memory to register. So it's essentially unrolling the bytecode and what the VM would have done if it interpreted the bytecode, but actually in machine code. So you can enable this option by putting a decorator on your function and say, please emit it using machine code instead of bytecode. It takes 2 to 3 times more RAM when you compile to machine code, but it runs about twice as fast, and you don't have to do anything, it just runs runs as though it's normal Python. The virtual machine is there and interprets the bytecode, and it uses the runtime to do things like dictionary lookups, as you would normally expect. List sorting and searching and all that kind of stuff. So the runtime is quite a big part of it, but it's sort of, yeah, it's not boring, but it's the less interesting of all the parts. Okay, so that's the core MicroPython internal, and then a given port, like Linux, for example, or a bare metal port, takes the core and provides a way to allocate memory, to do I/O, like printf, to load a file from a disk, and then actually has to provide an implementation of a rep or a prompt, because the MicroPython core has no concept of that. It can just execute code. You say, execute, parse, compile, execute this string. You can also implement custom modules for your own port. So, to go into detail about representation of objects to give you an understanding of how it minimizes RAM usage, these are not new tricks. They've been around for a long time, but implementing them in MicroPython was an important step. So an integer is represented, all objects are machine words, so say 32 bits for our example here. And an integer has the lowest bit set, and then the 31 upper bits are the actual value of that integer. So if I wanted to do 1 plus, so the number 1 is actually represented as the number 3 because the lowest bit is set. And then when you add two small integers, they still fit in a small integer, so you just return that actual value there. You don't need to allocate any memory. There's always a check whenever you do an addition or anything to see if it's going to overflow, and then if it does, it makes a big num, and then it needs to allocate memory, but you can't get around that. A string, so strings are also stuffed into pointers. If the lowest 2 bits are 1, 0, then the upper 30 bits represent a pointer to the intern string. Some strings are not interned, so it depends what you do. If you're reading in a file, you don't want to intern the whole file, so you don't do that. And if the two lower bits of a pointer are both 0, then the upper bits represent the actual pointer to another object on the heap. And then, as in CPython, the first element is a pointer to the type, and so on. And most objects are actually ROMable, so a tuple or a dictionary or a function or a module, you can actually pre-create this by just defining the right structure in C. And it doesn't take up any RAM. Okay, so I just wanted to say that, you all know how good open source software is, but open source software is very good, and GitHub is amazing, and we've been using this for MicroPython from the beginning. It's a public project, and anyone can clone the code and make pull requests and help develop it. We currently have over 1,200 stars, so we're doing quite well. We've got a lot of attention, and people are quite interested in what we're doing and following the project. And lots of people have been contributing from many different angles, so running it on Mac, on Windows, on Linux, on their own custom hardware, on some board that they made. So that leads to more robust code and more generalized code, because it's not just running on this board that I made here. It can run on many different pieces of hardware. And as you all know, a big project needs lots of contributors, and having an open source project allows such a project to exist. It can't just be a one-person thing. So the board itself, just to give you a little overview, this is what it looks like. It has on the back a nice little Python sitting on a chip, and some telling you what the pins all do. It has 192K of RAM and a megabyte of ROM for the actual binary, which is plenty enough. Runs at 168 megahertz. It has hardware floating point. It has an inbuilt, an accelerometer, so you can play around and work out the angle of the board. It's quite a lot of fun. And then there's an internal file system which is stored on part of the flash memory in the chip. So you can just do open/flash/test.txt or something, and it'll open and save it. And if you insert an SD card, you also have that available as /SD, and you can store files to that. So it's like a mini computer running Python on the bare metal. So it's just Python. You've got full control. You can disable interrupts. You can write inline assembler within Python. So one of the decorators of the function says, I want this to be inline assembler. And a function, add R1, R2, R3 allows you to, it actually generates the instruction, the thumb instruction, add R1, R2, R3. So you can really go to the bare metal with MicroPython and call inline assembler from within Python. And so as I showed you in the demo, you get a standard REPL prompt when you plug in USB, or over UART if you like. You can, if you don't have a USB port, if you have a traditional RS-232, that'll work as well. You can just type in commands and debug and prototype your thing that way, or you can put a little script on the internal file system and it will run that when it boots up. Or from the SD card, so I can put a whole sort of image on my SD card with my boot up script and my main script and all my libraries and configuration, plug it into one board and it will just boot up and run, plug it into another board and it will run exactly the same. So you have your whole system on a little SD card. And it can be powered by a USB, you don't need any electronics knowledge, you can plug it in and work straight away, or you can plug a battery in, or you can do many different things and it will run standalone. And so, just for my last slide here, talking about what the future holds, well, I don't know, but I hope that we can build a community around MicroPython. It has lots of areas that it can be used in. We need to, the documentation needs to some work, and that's something we're working on now. It's not just for bare metal, so it works just as well on Linux, Mac, Windows. You can compile MicroPython and just run it on the command prompt. It boots up very quickly because it doesn't have anything to do, everything's already in ROM. It has good potential for the Internet of Things, because if I'm making a little, a device to warn me that my fridge door is open, for example, it's easier to write, a program in Python to say if door open, tweet or email, than it is to write such a program in C. So that's a direction that we'd like to push MicroPython in. Also, following up from what was previously mentioned about why Python, or where Python can be pushed in the future, well, MicroPython is I think, ideal for embedding into games as a scripting language to drive the game, because it's minimal and it can be compiled straight away into your code base, and also for mobile apps. So because it takes up almost no memory, I mean, you can run code in 100K of RAM, and it would be quite useful for a mobile app. So those are things that would be nice to see move forward. If people are interested in helping and working on it, that's much appreciated. Please join us on GitHub. On the hardware side of things, at the end of this month we'll have another 3,000 Pi boards available for sale. So we sold out of the previous 3,000, and we've got another batch coming from our manufacturer Geltech in Luton. There'll be a light Pi board coming up, hopefully, which will be a smaller version. We want to give some boards away to people if they want to help us with documentation and writing tutorials and code examples. And then there'll be some extension boards which we're working on for just plug in a screen, and also this MicroPyB project, which is allowing you to add wireless extension modules to it, like an XB module, and other low power wireless things, so that you can communicate with lots of MicroPythons all over the place. And then ultimately also we want to incorporate some Wi-Fi connectivity, so you can just have a little Wi-Fi connected a board just there ready, and you can run your micro Django stack. Maybe. That would be cool. Alright, so thank you for listening. Micropython.org is the webpage. We have a forum and a GitHub page, and please join in if you're interested. Thank you. Okay, I think there's time for questions.
Thank you for the talk. It was very interesting. I have two questions. One question is about performance. Say you implement a for loop and that constantly switches on a GPIO port and off. So say a blinking LED. How many hertz would you get?
How many hertz? Okay. So if you ran it, okay, let me think. Yeah, it's a good. You probably get a megahertz or 2 megahertz. It's running on Yeah, you could probably get a megahertz. If you enable the native emitter, so it emits a machine code instead, then you can do very well with that, getting up to about that speed.
Oh, that's really fast. I wouldn't have expected that.
It can do quite well. And then if you need better, you just write it in inline assembler.
Right.
But no, if you're writing it just directly in Python, you can get, because it's running at 168 megahertz, the CPU, and the VM's pretty tight. We've done a lot of work with that. So if it's in a function with just locals and doing load fast, store fast, and then calling a GPIO on and off. So what you do is you would optimize. So I can show you on the board. Okay, so I would say, LED equals, say LED 1. Right, so you can see it'll go on. So you'd go LED on equals LED.on, like this. So then you could do allo, that would be optimized LED on. And then in the for loop, you just do allo, L off, L on, L off. And you would get close to maybe, megahertz. I can try that later, but
thank you. And the second question is, it would be great to have basically a network connection to the board, not only USB connection. Is it possible to connect it to, say, a Wi-Fi USB dongle?
No, not at the moment. So I agree. Internet would be amazing. There's a Ethernet module which we have, a WIZnet 5100, which is almost supported. Basically, open sockets, send, receive, HTTP requests, and so on. You can be a server or a client. That's almost working, but that requires the NAND module. There's also a Wi-Fi version, the CC3000, which is half working as well, and the same sort of thing. You just open sockets and so on, just like you would normally with sockets. And select is there and everything. And in fact, you can select on all of the peripherals, UART, SPI, I2C, Wi-Fi, so the way it's done. And you can use generators and so on. You can do quite a lot of stuff. But in terms of plugging in like a USB Wi-Fi dongle, that requires a lot of driver support, because those USB Wi-Fi dongles cost like £10 for a reason. It's because all the processing is done by the computer, this thing is just an aerial, basically. And so that requires a lot of extra work to get something like that working.
Okay. Thank you.
What are the features of the light version that's coming out at the end of the year?
The light version has so this board here, the microcontroller is quite powerful, and therefore cost a bit. It's got floating point hardware, digital analog to digital built in. It's got a lot of features, and it's very cool. But we want to make a more entry-level version with the light. The light version will have a tiny bit less RAM, half as much ROM, run at 100 megahertz, still has floating point hardware, doesn't have a DAC, so it's slightly stripped down, but it'll be a lot cheaper, and hopefully then it can be more widely adopted. But that's the main difference. It still runs the same MicroPython, exactly the same. It's just the hardware's a bit cut down.
You said that people had been running MicroPython on Macs on other computers. What sort of performance do you get compared with, say, CPython?
So it's not in our interest to compete with CPython, and as such we don't really run benchmarks just to compete. At the moment our interest is in making it work well and uses little RAM. But from the test that I've done, and most of the time it beats CPython on all the tests that I've tried. Mostly because of, it has really different structural internals, and it's just faster.
I'm kind of interested in the decision that you've made to have a parser and a compiler and everything on the board, rather than just having the runtime and bytecode dispatch sort of loop, and doing all the compilation before you download things onto the boards. Was that something that was considered? Or?
So from day one, the aim was to do this, have a compiler on board for the main reason that I didn't want anyone to have to install anything to use it. So a user just plugs it into USB, and then as long as they've got a terminal program like Hyperterm, on Mac it comes screen, you can use screen on Mac, you don't have to install anything, you just screen/dev/USB TTY. On Linux the same sort of thing, you don't need to install anything. You know, if I had to compile it on the machine first, I have to install some Python compiler, and different versions would, you know, you need to upgrade the hardware on the board and the software on the machine. I wanted it to be so easy that people could plug it in and Python was there straight away and they didn't have to do anything. So, you know, it also, when you plug it in, it appears as a flash drive. You can copy a script onto there and then it will just run. You don't even need to install a serial terminal. You can use Notepad and write a Python script and save it on the flash drive. So the main aim, it was for ease of use. And also, if you want to be able to execute exe and eval, you've got to be able to compile code on the board, right? So if you want real Python, you've got to compile code on the board. In the end, the compiler is actually not a significant proportion of the code. Most of it's in the runtime and the rest of the peripherals. But yeah, I mean, the compiler is a big part. So there's lots of questions.
Point at someone.
Over there. I can take more questions later on in person.
Hi, so when I was using my Kickstarter MicroPython thing, which was Delight, unfortunately, I broke it though, but
oh, really?
I'll get another one.
Okay.
So the sort of the deploying to the device, it seemed difficult to me, so I was mounting stuff, copying stuff over, or opening the file on the device, and then because I'm a rubbish programmer, I would crash it, and then I'd have to remount it, and so is there a better way to do it than what I was doing?
Most of the time I try and just use the REPL and just type in the stuff until, you know, just to get it working. But yeah, to write a function on the REPL is not the most fun. So yeah, you write it in some code and then you have to mount and copy and then unmount. And because if it crashes, yeah, you have to remount the flash drive. I don't think there's an easier way than doing it. One thing we're trying to do is make it so you can run that code on your PC first, because it's just Python. So you run it on your PC, make sure it works. We just need to make some bindings for the Python board modules, like the LED, you know, make a fake LED class.
Yeah, if there was an on-screen fake LED.
Yes.
Or let's say a simple deploy script, so I can do tips or whatever, push and reset the device in one button, not have to worry about mounting it all work via this easy one, and it can be sent to.
Yes, actually, and now I think about it, there is one way to do this. I did write a script so that you write your script on the PC, and then you run this program, and it copies the script to the board, runs it, and then gives you the output without rebooting or anything. That would actually be really useful for you. It's in the tools directory, and it's used, for example, to run all the tests. So you can. So this will run all of the tests on the board. So it's going through them now. So what this does is these tests are just written on the PC, and it just downloads them, runs them, gives you the result, makes sure it matches with normal Python, and then moves to the next test. So yeah, it's called pyboard.py in the tools directory.
Thank you very much.
Okay. How much? So the version is £28. Currently, we say hopefully at the end of this month, and then the light version, when it comes out, we hope to sell for £20. So keep a look on micropython.org.